All right, great. So so my name's Mihir Paradkar, and I just graduated from Cornell University. And I'll be talking about making sense of messy data with GraphGLRM.jl. So before I start, I'd like to thank two awesome people in particular for getting me up here and making this happen. First, my research advisor, Professor Madeline Udell at Cornell, for inspiring me to learn all the optimization, her patience in answering all my questions, and for letting me use some of her lecture material for this presentation. And second, I'd like to thank my dad, Dr. Amit Paradkar at IBM Watson Research Center, for making me a better presenter, because he says he'll shoot me if he catches me reading off my slides. So we have to answer three basic questions. I'm going to answer one, what is big messy data? Two, what is GraphGLRM? And three, why Julia? So first, what is big messy data? So I define it as data that's omnipresent or everywhere. It's heterogeneous, so the values in the data can take on multiple different types. It's impure, meaning that it's got noise, it's got missing values and other impurities. And it's interconnected, meaning that it comes from different sources, but those sources are not independent of each other. So how many people have been to a doctor's office? So electronic medical records are a very important form of, and growing form of big data. They contain measurements taken by nurses and clinical notes, as well as images that might have been taken for other measurements. Anything on social media and a lot of text data is also vital in today's analytics world. So, this is just a word cloud representation of various social networking type of words. And images are another example of data that's everywhere. All of these things can be analyzed and patterns extracted out of them. So that means that a sophisticated method should be able to handle data regardless of the type of source that it comes from. So the next challenge is that data is heterogeneous. So there's a few different data types. The first one, or the simplest, is the Boolean values. So for example, a yes or no, or in biological sexes, male, female, et cetera. They only take two values. There's also categorical values, which can take the values such as red, blue, and green, or A, B, O, and B in blood types. And these don't have any kind of hierarchical relationship with each other, but they encompass a set of more than two values. The next on this hierarchy is ordinals, which have a hierarchy, but without necessarily knowing the distance between values. So examples are stages in cancer. Like we don't know that stage 3 is as much worse than stage 2 as stage 4 is to stage 3, but there is a hierarchical relationship there. And finally, we have the real values that we all know and love, like physical quantities such as temperature or concentration, as well as amounts of money can be represented as real values. So that means that type awareness is critical to being able to utilize all of our data effectively. Data is also impure. So some examples are the infamous NAs in data frames. Here we have people that didn't complete their surveys, but there's also examples like sensors malfunctioning. Images might be occluded, or people might be wearing sunglasses in facial recognition systems. And text data sometimes can't be parsed or even tokenized properly. So we should be able to figure out the values of missing observations from the observations that we already have. And finally, data sources aren't independent of each other. So for example, sonogram images taken prenatally are related to electronic medical records that are written up at birth. So this is just the example that I can think of because my research involves dealing with neonatal medical records. So other examples include time series data, where the values for 1963 should be, are related to the values from 1962 and 1964. So that means using knowledge of similarity between your data sources, whether separated temporally or in type of measurement, is vital to being able to make more sense of your data. So that means a solution for modern data should present a compact representation for any sort of data. It should be aware of the data type you're dealing with. It should be able to handle impurities and missingness in your data and utilize the knowledge that the sources of your data are independent. Which brings me to my next point: what is GraphGLRM? So it's available on my GitHub and as a Julia package. I felt that was obligatory to explain. So it consists of two components. One is the generalized low-rank model framework developed by Professor Udell and plugged in her last talk. And the second component is the graph Laplacian regularizer. So first I'm going to be giving some background to low-rank models. So the basic idea is that if you have data that can be approximately represented as a matrix, so for example, a data frame or a matrix or a sparse matrix, then we can compress it into two low-rank factors, a narrow factor and a wide factor, where the rank is how thick this narrow factor is. And the idea is that one of these factors is a compressed representation of the examples in your data, or the rows, and the other factor is a compressed representation of the columns, or the features. So the advantage of this approach is that smaller matrices are easier to manipulate and store, and they help avert the so-called curse of dimensionality in machine learning, which is that when you have many, many variables, it exacerbates the effects of noise in your data. These also work on a variety of data sources like sparse matrices and data frames, which is key to versatility. However, when we say approximate a data matrix as the product of two low-rank factors, we must ask, what does approximate mean? So this is where we get into handling different data types, because approximate means different things depending on what your data is. So the first example I'm going to give is using the quadratic loss function, or mean squared error, as your metric. This recovers the truncated singular value decomposition, or PCA, in a special case. And the objective function there is just the objective function for those of you who are familiar with PCA. However, we don't always want to use that, for example, on Boolean data. So the reason for this is that sometimes we might want to encode Boolean variables as real values, and we just care about whether the sign is right or not. So the more positive your value is, if your data point is true, then you don't want to penalize that, whereas the quadratic loss function does this. And that's what the arrow is pointing to, the penalization of your model being too correct. So this is similar to the principle of using support vector machines and logistic regression on binary data for classification, and the reason why you don't use least squares. So we also include loss functions on ordinal and categorical data, such as the one versus all loss, and this is you can find this in the documentation for low-rank models. And an additional advantage that for data frames, which have multiple different columns that can be of different types, we also implement having one different type per column so that you can better use the data that you have in your data frames instead of trying a one-size-fits-all approach. So now I'm moving to how we handle missing and noisy data. So here is a representation of a data frame that has missing values, which is the black square. So the way that this works is that we're approximating as a low-rank factor, and as we're training this model, we try to best approximate each value, so the circled point in the original data, as an inner product of a row of our narrow factor times the corresponding column of our wide factor. And we train to minimize this loss function with penalties. After doing this, we can then have a good estimate for a missing value by simply, again, taking the corresponding dot product. So we also support robust loss functions, such as the L1 loss function, which penalizes outlying values, or very large values in our data. This is directly related to how the median is more robust statistic, and so is used for reporting things like income, because there are fewer, it bends less to outliers than the quadratic loss does. So in the problems that I deal with, for example, doctors might switch the birth weight and gestational age, leading to a gestational age of 2 weeks on a baby or a birth weight of 33 kilograms. So we don't want to make these outliers affect our analysis too much. And finally, we include regularization penalties and other forms of constraints, such as non-negativity or the sparsity penalties, like the L1 regularizer. And the way that these work is by imposing a prior distribution on our low-rank factors that help the data take a more believable structure. So that's just a very good illustration that I found about this. So now the second part of this GraphGLRM is the graph Laplacian regularizer, which helps us take into account similarity between different variables that come from perhaps different sources. So at a high level, the way it works is by treating your columns or rows as nodes in a graph. So two possible applications of this are linking blood pressure measurements taken from different sources. So in this case, by a cuff and by a UAC. But it can also be used for linking variables that are different across time, such as the Apgar score at 1 minute or 5 minutes. And so the regularizer essentially works on one of these low-rank factors by treating them as nodes on a graph and encourages the ones connected by an edge to be closer together in value by penalizing the sum of squared differences. This is all a mouthful, but I'm going to be explaining it in subsequent slides. So some properties of the graph Laplacian matrix that many of you may already know are that it's symmetric with one column per each node you have in the graph, and the diagonal entries correspond to the number of edges going into a particular node, with the off-diagonal entries being -1 at any I and j where node I and node j are connected. But I found that the best way to learn this was through some examples, so here we go. So this is a path graph, which is useful perhaps in time series data where you want data for subsequent years to be related to each other, but and that provides a simple encouragement for that smoothness to happen. So this is a fairly simple Laplacian matrix with 2 on the diagonals in the middle and 1 on the diagonal in the edges because they only have 1 edge in the first and last node, and -1s on the diagonal immediately above and below the main diagonal. So now we can have a cycle graph where the first and last nodes now get a second edge connecting them. And this influences the bottom left and top right corner of the Laplacian matrix. And another example is the complete graph, which is fully dense and has -1s on every off-diagonal entry with the number of nodes -1 as the diagonals. So the reason that these particular graph forms are important is also because oftentimes data requires combining multiple of these subgraphs in a clique structure. So for example, one cluster of variables might be connected by a complete graph, while another set of variables might be connected with a path graph. And this just creates a block diagonal structure on the Laplacian. So the way we use this is by using a special quadratic form. So here's an example because I find that very helpful in intuitively understanding how this might work. So here we have 2 different low-rank vectors. So they're matrices of rank 1. Where the one on the left is smaller in magnitude, but the one on the right is smoother in its entries. So the first 2 entries of that vector are the same. So despite this difference in magnitude, you can see that the quadratic form is smaller in the second case than it is in the first case because they're smoother across the edges. And a generalized version of this quadratic form is what we use in the GraphGLRM. So the final form is this objective function for a GraphGLRM. And the important bit is that we use a very similar quadratic form on the wide factor, or you can also use it on the narrow factor. So the motto of GraphGLRM is, in terms of imputing your data, is it's not how big your data is, it's how you use it. So now I want to move to the third question, which is why Julia? So I found that it has a very elegant syntax with a very rich type system, which is a rare combination in the technical computing world. So here I've highlighted a couple of examples, like the implicit coefficient multiplication and the Unicode functions, which make your math code shorter and more readable, which is a very rare combination. And this code here is just some initialization code for the low-rank factors, which does a truncated singular value decomposition. And in the rich type system is also incredible because it means that you can express linear algebra operations on, say, a diagonal matrix as if it were a full matrix, but it only has to store a single vector, both making it more performant and more readable in implementation. So another reason is that user code performs just as well as library code at near native speed. So here's some code that I wrote for computing the gradient in fitting this. And here we have an anonymous function that takes an arbitrary loss function object. However, this anonymous function performs just as fast when mapping it across different arrays as something like sumabs or sumabs2, whereas in something like NumPy, this is simply not the case. And it has a rapidly growing package ecosystem and community, you all. And that makes it really special because every time that there's been a new release, there have been incredible features added, like the dot broadcasting and loop fusion. But Julia can call Python and C libraries when strictly necessary. PyCall is one of my favorite packages, and we use scikit-learn's hooks to Python for a lot of downstream analysis after using our GraphGLRM. And of course, when I talk about Julia passionately enough, they think I have a girlfriend. That's Julia Louis-Dreyfus, by the way, from Seinfeld and Veep, who comes up on the Google search results sometimes when I'm trying to debug my code.
To be clear, Julia does not have a gender.
So I've learned a lot while developing this package. Particularly, GraphGLRM has worked surprisingly well on a variety of problems. But we could optimize some of the common cases more. And I think Julia language has a lot of unexplored potential from what I've been writing and learning along the way. So this is an example result from when we applied GraphGLRM to image data. So the first is a face of the. So this comes from the Olivetti Faces dataset, which has 400 images of 40 different individuals with 10 images each. So we occluded a block of the image, and this one happened to get occluded over an eye. So the second image is an ordinary in-painting algorithm from OpenCV, and it looks kind of scary. I know that my DSP professor told me he had nightmares about that one. The third image is what happens when you reconstruct this library of images with GraphGLRM, and it really gets its power from that library of related images. That's how it can learn that there should be an eye in that block of pixels. And of course, the last one is the original. But it could still be more optimized in a few cases. So for example, with dense matrices, as you might find with images, we could optimize it a lot more for a single type of data and fitting that much faster using more BLAS operations. Whereas in the recommendation system on the right, which is just a screenshot from Amazon, this is often a very sparse matrix system because most users don't rate most products. And therefore, we could exploit sparsity structure a lot more in solving these problems. We currently optimize for the data frame case when we have multiple loss functions and multiple different types of data. And I think there's untapped potential everywhere. So this is a case that I saw when I was working on making this faster for fitting on images. Advanced performance documentation would be incredibly helpful. And this isn't a complaint. This is just something that I found and I think I could do a lot to improve. So the example here is that when we have missing data and we're trying to iterate over it, skipping over missing values creates a lot of performance issues because the data is because you're not accessing elements contiguously. So I figured out that you have to copy that into a contiguous data structure, and despite the extra copying, it pays off a lot of dividends. I got up to 7 times speed increases from improvements like this. So documenting things like the trade-off between copying and contiguity, it could be worth it, is something that could be very useful to prevent new users from having to struggle for weeks on end to figure out how to speed up their code even more. But I think it's a very promising language, and that's why I still always keep coming back. So let's show the world what Julia can really do. And with that, I ask, are there any questions?